Y hat, Z hat.
I don't remember the hat, but, yeah.
In physics, the hat is telling you that it's a unit vector, so what it's there for is to tell you the direction. So I hat, J hat, K hat, or X, Y, Z, the X direction is whatever you say the X direction is. Now math people always try to convince you X is that way and Y is this way, but if I have something going down a ramp here, it'd be a lot more convenient to make that my positive direction and that a positive direction, as opposed to doing everything horizontal, vertical. That's why I prefer I hat, J hat, K hat, because people are so brainwashed into X and Y that it throws them off when we want to go set our coordinate system like that, or box on ramp. I'm willing to bet you did a box on ramp problem.
Yes.
Whether you remember it or not, I'm willing to bet you still did
We
one.
did that.
Yes, we did.
All right. R hat is a little bit different unit vector. The only choice I have about the direction of R hat is what's the center. The radial unit vector has some center, and then R hat is away from the center. If I want to talk about something that's pointing towards the center, how do I indicate the opposite direction?
You flip the hat upside.
That would be interesting. That's not the way that they chose to do it. What's the other way you do opposites?
Negative.
That's the one. So negative R hat means towards the center. Potentially you saw this in 131 when you covered centripetal motion. Now some people throw in the formality of it and some people don't. When he is here, the force of gravity is towards the center. So when I plug F equals ma, it's negative big G, mass of person, mass of, looking at that one there, R over big R cubed, little r, R hat. That's the formality. This is my magnitude right here that I've just boxed in, and the negative R hat tells me it's towards the center. That's going to be equal to mass times acceleration, the mass of the person times acceleration. We can simplify it. Just a little bit. The mass of the person cancels out, which is just as well because you're typically not given this mass in a problem like this. The acceleration would also have to be radial. I can rewrite this one as, so now I have negative big G mass of the planet over big R cubed times little r is equal to whatever the acceleration is, R hat. Oop, that was my R hat on the left side. They both have to be radial. It's not like he's falling and there's acceleration off to the side. Oh yeah, I guess that's one other assumption is I assume the Earth's not spinning. Unless he's doing pole to pole.
Question.
Was that? Yes.
The Earth is not completely, because it's wobbling. If you say it's not wobbling or spinning.
Right, right. I am simplifying it to make it solvable.
So is it really Earth then?
Then what?
So is it really Earth then?
He's on some mythical planet, which happens to have the same mass as Earth and the same radius of Earth.
And the density is completely the same throughout the whole.
Yeah.
And there's no air resistance or friction.
It's a magical planet. It's the same type of planets that have acceleration of gravity equal to G, equal to 10.
And spirit don't have no heat to
There potentially could still be heat there.
Let's just assume
Depends on if there's radiation coming from the rocks.
Let's just assume the guy is wearing a suit that makes him immune to heat.
You know,
Because the heat
Just
would,
be dead.
because you wanna have pressure there
I
too.
think what I'm getting here is a sense that this is not a realistic problem, and
No, cause you got pressure too.
Well, this is a mythical planet.
Yeah, so,
yeah.
Well,
He's wearing a suit, all right,
What I was wondering
and
was,
tie.
if there is air resistance, wouldn't you reach terminal velocity?
It depends upon what the density of that is, it's possible.
And if
If he's going fast enough, the resistance is directly proportional, air resistance is directly proportional to his speed squared. Now, the question is, if that ever matches the gravitational pull, see, if you're above the earth, gravitational pull is roughly the same your entire fall down. You do reach terminal velocity in that case, because the density of air is enough that you hit enough air. In our mythical planet,
But like,
That'd be a
what
nuisance to solve.
we were saying earlier, like, would he even reach the end of it? If he was going terminal velocity, which I think is like 120 meters a second, or something like that, he would slow down and move back toward the center before he got to the end. Because
he would eventually,
he would get like, I don't know, 3/4 of the way down and then just keep going back up.
and then he basically would oscillate back and forth and eventually settle in the middle.
Yeah, he wouldn't even make it to the end.
No, he would not. That's why we throw in the no frictional resistance. All right, connecting back to simple harmonic motion. So I've got these two sides here that are equal to each other. I can get rid of r hat, because these coefficients must be the same. Now we have a formula here where the acceleration, I need some solution, because I know acceleration and position are related to each other, which we talked about before, the last 2 weeks ago. And there's the negative there. So I just need some formula for r such that its second derivative, or the slope of the slope, the acceleration, is basically equal to the same function, except negative. And we went through that last time. So if r is equal to some amplitude times the cosine of omega t, then his velocity would be negative a omega sine omega t, and his acceleration would be negative a omega squared cosine omega t. We did not explicitly start out with Hooke's law, but we came up with a relationship which matches Hooke's law, the fact that acceleration is directly related to the negative of the position.
Is
So-
that omega?
Pardon?
Yeah, that's okay.
That's an omega, yes. So if I plug into there, I get negative big G mr, or plug into there, over big R cubed times a cosine of omega t is equal to negative a omega squared cosine of omega t. That's my acceleration. That's my position. Now we cancel stuff out. The amplitude is the radius of the Earth, but it cancels out anyway, so I don't have to worry about that. Cosine omega t, can't get rid of that. The minus sign I can get rid of. So I'm left with omega squared is equal to big G mass of the planet over R cubed. So omega is the square root of G mr over R cubed. The frequency is omega over 2 pi. Or better yet, the period is 2 pi over omega. So the period of dropping through should be equal to two pi times the square root of big R cubed over big G in R. And can we now plug in numbers and actually get the value for the period? So the period is two pi times the square root of the radius of the Earth, 6.38, or whatever planet this is, times 10 to the 6 meters cubed, divided by big G, which is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, times the mass of the Earth, 5.98, times 10 to the 24th kilogram.
Two pi. The square root. 6.38.
Oh, that's a
Well, it's
mistake here.
2.8.
That should be negative 11, not negative 7. I said Slurpee's on my mind.
Times 10 to the 6th. Cube. Divided by.
Oh,
Times 10 to the negative 11. What's that in the middle?
What's that in the middle? This
Right, yeah,
units, Newton meter squared over kilogram squared.
okay.
I don't know how right this is.
What'd you get?
5,069.87 seconds. Seconds. But that doesn't seem right to me.
Anyone else get the same thing?
That seems too small to me.
How many minutes is that?
Hundred, what, less than 100,
Okay.
around.
85 or 84.497.
A little under an hour and a half.
Alright, I got a really big number.
What'd you get?
7.94, those 10 to the negative 4.
The negative 4?
Yeah, to the minus 4. Yeah.
That's a really tiny number. So you have it under a second.
Yeah, that's all I was just like, yeah, I don't think I did this right.
Trying to think how you would get that. The two most common mistakes, and I don't know what happened there, I feel pretty confident this is not right. Some people, when they're doing the division here, forget that you're actually dividing by this also. But that would have actually made your final answer a lot bigger.
Yeah.
Potentially didn't cube it, but usually the mistake there is to forget to do that at all, which would have made your answer.
Where did the 6.67 times 10 to the negative 11 come from?
Oh,
It's the gravity.
the value of big G. It's the gravitational constant.
I got the 5,069.
Okay, we have two for that.
For some reason, I was thinking it was like way bigger than that, like 25,000 seconds.
So, silly, I mean, you're still looking at it. Did you catch where G, this came from? Or do you want more?
You already.
Not exactly.
It's the gravitational constant. It is a constant value. It comes from the tedious experiment that Robert Cavendish did in the 1790s, where he took a mass, basically, he had a mass dangling from a thread. And then next to it, he put two other masses on a stand. So these were put into a set place in this airtight container. And then this would start to twist. So from whenever it, he needs it to twist. So from an overhead point of view, you've got the two masses. You would have to put it. He had it set up so that this would twist. And they knew how much force it took to actually twist this thread here. And then he would, I believe, the way it's always described is that there's some mirror or something like that, so that he shines a light on it, and that light shines over here, and then he sees how far that light moves, so he knows how much the string is twisted, and therefore knows how much force was applied, and then measures the distance between them, and basically use that formula that we had written up here for the force due to gravity, and calculated what big G was. That's how they came up with it.
So that's the.
Yeah, we could do it now slightly differently, but that's ultimately where it came from. Now, and then, so ultimately, the value of it depends on what units we're gonna use. So this just happens to be what the units are when you're dealing with international standard units.
So that's the amount of time it takes for him to get to the other end of the earth or to the center?
That's the period. That's how much time it takes for him to get back to where he started. So therefore, the time it takes for him to get to the other side would be half that. The time it takes for him to get to the center would be a quarter of that.
Oh, that's really small. That's not
So-
big at all.
Roughly 42, a little over 42 minutes to get to the other side, and a little bit over 21 minutes to get to the center.
But that's, is his acceleration, does he just keep accelerating?
He will be getting faster and faster, but the rate at which he's getting faster starts to slow down. So so he is getting faster, but right before he gets to the center, he's not, the change in speed of 10 meters from the center and 5 meters from the center is not a whole lot different.
But like, there's no air resistance, so
Right.
he's just gonna keep accelerating toward the center until he gets past it, then he's gonna slow down.
Right, and still officially he's accelerating towards the center. Just that because acceleration and velocity are in opposite directions, he slows down.
Like I said, I thought that was like supposed to be much bigger, which, I mean, I guess it would if this was Earth, like actually Earth.
Oh, if we brought more reality into it?
Yeah. I mean, what, just getting to the center of the Earth is only gonna take like 20 minutes? That's,
Yeah, well, think about the longest fall you've ever had. I would assume, for me, it would have to be part of an amusement park ride where, they strap you up, they pull you back, and suddenly they let go, and you get that moment of free fall before you start to swing. Or if you've ever bungee jumped.
but that's like 3,000 miles though, that's a long fall, that's like really long fall.
I think if you were falling for 21 minutes, it would seem like a long time. And the time it takes to watch a half-hour show with no commercials, you reach the center of the earth.
I mean, think about that, you can fly from here to Atlanta in like an hour and a half, and you can get to the center of the Earth in a fourth of that.
Yeah.
Falling.
Yeah.
That's crazy.
Still doesn't seem right?
No, it doesn't seem right, it's too fast, you
Yeah, if you
go like
got,
500 meters a second.
yeah, if you gotta think, you're going, when you're flying, you're not going in a straight line like you are at center Earth. You gotta go up, and then come all the way back down.
You always
Distance is a lot
vector,
greater than you actually think it is.
All right, but let's look at it another way. You start out, when you take that first step, your acceleration of gravity is just a little under 10 meters per second squared. Which means that your velocity changes, the change in velocity or change in time is about 10 meters per second every second.
Mhm.
So if that were constant, and it's not constant, but if that were constant for the first minute, you'd be going 600 meters a second,
Mhm.
which is about
23
1,200, it's a little over 1,200 miles an hour.
So like 0.3 miles per second.
Oh, what that is, or no, 1,200 miles per hour, oh, yeah, 1,200 miles per hour.
1,200 miles, or no.
So about a third of a mile per second.
Yeah.
That's in the first minute.
Yeah.
Yeah.
Now, the rate at which you are speeding up is going to decrease the closer you get to the center. But if you think about, if I'm here on the surface of the earth, so G is about 9.8 meters per second squared. If I am 100 kilometers up in the air, the acceleration of gravity, I think, is around 9.2 meters per second squared. So 100 kilometers from the surface of the earth, the acceleration of gravity does not change significantly. I suspect for the first minute, it's not changing significantly. So anyway, if you find it unbelievable, then you will leave on that unbelievable idea that it only takes a little over 21 minutes to reach the center in our nice ideal situation.
That's a lot of time.
You probably get there faster if the core is denser than the crust, which would have to be because the crust floats on top of it.
Mhm. But you'd also get there slower if there was air resistance.
True.
Because because of terminal velocity.
If you ever reach it. It depends upon the density of the air. If the air is rarefied, you know, we're already coming up with sort of a fantasy here. So if we've dug this huge hole in the ground, is the density of air greater the farther down you get?
Well, it's denser the closer you get to the surface, so.
Yeah,
We can
but-
assume that it's probably at least surface level dense.
Not necessarily, because if we bring in the spinning Earth, which obviously we ignored earlier, but if the Earth is spinning, then air would have a tendency to move